Hello ladies and gentlemen, and welcome back. So in this video we're going to kick off our look at Simplex 2D noise with a little bit of theory. Now, I have not yet seen what Lee has prepared. Often I get to see a little bit of a sneak peek of some of his R&D stuff before we begin recording a video. In this case I haven't. I've just listened to Lee moan and groan a lot about having to make it through the explanation of Simplex 2D noise. So this should be very entertaining for those of you out there watching the video and myself as we kick back and hand it over to Lee. All right, Lee, teach us.
The Simplex 2D, yeah, that's a fun one, but not quite as much fun as the 3D Simplex. I mean, anytime you have to pull out Maya and start modeling and animating stuff so you can figure out what's going on conceptually, that's when things get interesting.
So we're about to start ramping up, though, in this video compared to...
Yeah.
Okay.
Everything up until now was just a warm-up, try to get you, a little bit ready for what was coming.
So Simplex is done by Ken Perlin.
Yep. This was his way of working around some of the issues with Perlin and improved Perlin. And so the last noise that he came up with officially is Simplex noise.
Okay.
But, he's got some pretty interesting experiments that he's always working on his website. And if you do a little Google search, you can eventually find his homepage. Mm-hmm. And he's got all kinds of different little experiments, and he's always playing around with stuff.
That's cool.
So, but he's by no means just did these three noises and said, "Oh, I'm done. I'm not doing anything else." So he's always playing around with new, pretty cool techniques and technologies in some respect. But the big thing, why Simplex? I mean, we already saw that value noise is blazingly fast. Mm-hmm. It's even faster than Perlin noise. But with implementing Perlin noise, we also see that Perlin's a bit slower, but it definitely looks better. So the reason we're going to look at Simplex is while in the 2D case, value noise is still faster, in the 3D case, Simplex and value noise are about the same. Both of them are faster than Perlin, but the nice thing is Simplex is another type of gradient noise. So while what we get looks different than Perlin, it is still a gradient noise and looks significantly better than value noise, in my opinion.
So you still get the organic, fluid-like feeling.
Exactly. We get that the convection or the organic rolling type of animation as we roll through the 3D Perlin noise.
Awesome.
So we get that look or that feel for the performance speed of a value noise. Mm-hmm. So now the trick is how that's actually arranged or how we accomplish that. And the way it's accomplished is if we were to compare value noise, where value noise has to calculate 4 different points and average those together or blend those together to get your noise. Mm-hmm. Simplex noise works by in 2D by only using 3 points of information. So you're using 3 gradients to accomplish what value noise takes 4. So the return
gradients? Value noise uses gradients?
Well, no. Simplex uses gradients, but
right.
It uses 3 gradients to give you the same effect that value noise, where they have to do 4 samples.
Okay.
But they're not. Value noise is using lookups.
Right. I know. You just said gradients for value noise. That's I just.
Nah, I said it for Simplex. But
okay.
We got video evidence we'll never look at. But we'll go with that. I confused it. Value noise is lookup, and Simplex and Perlin are gradient noise based.
Right.
So basically we have a curve that we're using to look up a value at a point. Now, the nice thing or the really cool thing about Simplex is the higher orders of Simplex noise, higher orders being 2D, 3D, 4D, 5D, 6D, etc., and on and on and on and on. The higher up that you get in dimensionality of Simplex noise, the more effective or the bigger cost savings that you get for the calculation. So if you look at value noise, or for that matter, Perlin noise, 2D in both value and Perlin take 4 points of calculation. 3D take 8 points of calculation. 4D in both, I think, is 24 points of calculation to get 4D.
I thought it was 32, but
it might be 32.
I could be way wrong. This isn't my field. Anyways.
Yeah, well, once I started looking at the complexity of 4D, I said, no, thank you, and stepped away. So 3D, so I didn't delve very far into what makes up a 4D noise. Now, the nice thing with Simplex, though, is the cost of calculation, or the points of calculation, is the dimensionality plus 1. So for 2D noise, your samples are 3. For 3D noise, your samples are 4. For 4D, your samples are 5. So it's a bigger return the higher up in dimensionality that you go. Now, the way this works is by using something called a Simplex grid, which is basically a simplical, I can't say that word either, tessellation of your n space being 2D, 3D, etc. Now, what a simplex is in this term is basically the simplest, most compact shape that you can use to subdivide an object of that space. So in 2D, the simplest shape that you can use to divide up a 2D plane is an equilateral triangle. Where in 3D, and a triangle obviously has 3 points, so hence your 3 sample points. The simplest shape that you can break up a 3D shape into is it basically looks like a squash tetrahedron. So it's basically a squash pyramid that has 4 sides, or 4 points, not 4 sides. Oh, yeah, it would be 4 sides. Or no, 1, 2, 3 sides, 4 points. So, but that's the simplest shape that you can use to make up the space, hence the 4 points of sampling. Now, the way we can visualize this, if I jump over into Photoshop, let me bring up before I do get into Photoshop, where I'm getting most of my information. Yes, Ken Perlin does have information on simplex noise, and it's not very easy to understand, and he's got source code that is even harder to understand than his write-up on simplex noise.
Wow.
Where I found all my most useful information is, once again, the Simplex Noise Demystified paper by Stefan Gustafsson. So once again, I'm butchering names. I apologize. But inside of here, apart from the really good discussion on 2D and 3D Perlin, we start getting into discussions on simplex grids, what a simplex is. Here's our tetrahedron that's been squashed. And then it gets into 3D. Doesn't really get into 4D, but it does a really good explanation compared to anything else I've found on the website. But even then, I had to bring out Photoshop and start drawing stuff for myself to understand it. And then when I moved into 3D, I had to bring out Maya to figure out what was going on.
Mm-hmm.
So, but I'm going to try to convey what is written in that paper the best I can using Photoshop and Maya.
Okay.
Try to help. Now,
what, by the way, did you say a second ago has 4 points but only 3 sides?
A tetrahedron. So it's basically a pyramid, a 3-sided or a 4-sided pyramid, or 3-sided pyramid.
Okay. You're talking in 3D space?
In 3D space.
Okay. My brain has been stuck in 2D space for this whole conversation, and when you said that, it kind of hit in the back of my head. I was like, 2D, what kind of shape has 4 points but only 3 sides? No,
tetrahedron 3D space.
3D. Okay.
I was foreshadowing what we're going to get into. All right, so let's draw up a simplex grid real quick. It's pretty bad when you go, yeah, simplex grid, no problem, I can draw one of those. And those of you who are going through the train R&D might recognize this shape. Because I did kind of use it for the basis of something else. So if I turn off the guidelines, that is a two-dimensional simplex grid. It's not perfect because with Photoshop it's really hard to make equilateral triangles really fast. But let's pretend each one of these is an equilateral triangle. And for those that were listening, this is how I designed the train grid layout for all the vertices. So this is pretty much our train. But what a simplex is in 2D is each one of these triangles. Each triangle, if I switch over to our so if I just draw up, come on, there we go. And no pixels were selected. I don't want pixels selected. Let me pick a different color too. Red works. All right. So each simplex has its own point. Now the way this works is we're going to once again be relying on gradients because simplex is a gradient noise. So if I create another layer, and let's do black to transparent, that should work. And I need a radial. But the way these work is our gradients will never cross another point. So they're as large as an area needs to be, or it needs to be, without ever hitting another point. So if I were to bring down the opacity to this, let's say to about 20, let's do 50, a little bit easier to see. And then if I were to take this, duplicate it, whoops, Control Z. In order to center this one up over here, duplicate it again. Let's try 75. So what we're doing is we're taking each one of the points on our simplex grid and we're giving it a gradient that goes from black to white. And then if we have a point somewhere inside of our grid, let's say, for sake of argument, this is our point. So if I fill that with black. So if we have a point inside of our grid, what it does is it calculates which simplex on our grid that point exists, figures out a gradient to put at each one of these points, and then looks at what the contribution is of that gradient at each point, and then calculates the color at that point, or that value at that point, and returns that. Now the neat thing is we don't have a simplex grid, but the neat thing about a simplex, the simplex grid is virtual. We're not really relying on it. But if we were to take, say, one of these diamonds that is formed by a simplex grid, so if I hide all this out and turn my guide back on, make another layer, and then I take my line tool out. So let's say we pick on this diamond right here. So what I'm doing is just tracing out its outline. Now if I hide out here, we've got this diamond. Then technically it has a point here going across. So if I turn off, here's our diamond. Now, in essence, what we're doing is we're taking our unit square from what we've demonstrated in both value and Perlin, where a square has its start point and it's 1 unit high by 1 unit wide. What we're doing is we're taking our grid, we're going to transform it,
and shear it.
and we're going to skew it.
Or skew it, yeah.
Yep. So if we take this, and because these aren't equilateral triangles, it's not going to be a perfect square when we're done with it. But if we skew it, we get our unit square. So the way we're going to do this is we're going to take we're going to make our virtual simplex grid, which is just going to be a mathematical space. We're going to skew it so that it becomes a unit square. We're going to test our x, y, and figure out which one of these simplexes that our point exists in, and then we'll skew it back, and then we'll use the calculations for drawing our gradients, and then get our contribution for each of our points, calculate what that contribution at that point is for each one of these, and then average those three together and return that value back out.
Okay.
And that is how simplex noise works at its core.
Oh, that's very cool.
So,
well, is that pretty much all you wanted to talk about as far as the theory for Simplex 2D goes?
Yeah, that's pretty much it without getting into a bunch of complex math. But for that, you can look at the paper. And then we'll also look at how that's really implemented once we get into the code, which will be the topic of the next video. But once again, if you want to get the more technical discussion on it, that's all inside of here. And you can see where they're talking about the simplex grid and how the gradients have a contribution that do not overlap any other points.
Awesome.
So just a different explanation. There's different diagrams about how it skews everything to fit into the unit square, like I was trying to demonstrate in Photoshop. So there's that. And then at the very bottom, there is the Java code that we're going to be using. This is, again, my implementation of Simplex is pretty much completely pulled from this paper. I'm just modifying things as needed to make it work in C# because this was written in Java.
Okay.
So, but other than that, that's what I wanted to cover for the theory of 2D Simplex.
Fantastic. All right. Well, that will wrap up this video, and we'll see you guys in the next.